Mm-hmm.
So I'd like to thank you, Professor Cristiane de Morais Smith, for have accepted the invitation for this lecture. My name is Marcelo Magra Amaral. I'm from Universidade do Brasil, and I will be the chair of this section. And let me introduce Professor Cristiane de Morais Smith. Professor Smith is professor at Institute of Theoretical Physics at University of Utrecht, Netherlands. She is a worldwide recognized researcher working on theory of strong correlated systems. Professor Smith was awarded with the Winter 2019 Emmy Noether Distinction of European Physics Society for her outstanding contribution to the theory of condensed matter systems and cold atoms to unveil the novel quantum states of matter, and the 2016 Dress-Hall Prize of Hamburg University for her outstanding contributions to the understanding of topological phase in two-dimensional atomic and electronic systems. Her research interests range from condensed matters to cold atom systems. In collaboration with experimental colleagues, her group has pioneered the realization of quantum fractal and higher order topological states in electronic quantum simulators. Her group has also set the basis for a thermodynamic description of topological isolators and superconductors, and actively contributed to the development of a projected quantum electrodynamic formulation to investigate topological phases driven by interaction. She has published more than 130 papers, including Nature, PRX, and PRL, among other high-impact journals, and was invited speaker of more than 300 talks and conferences and colloquiums in 18 different countries. Today, she will share with us a little bit about her research in her lecture entitled Atom-to-Atom Engineering of Electronic States of Matter. Please welcome Professor Cristiane de Morais Smith. You can share your screen, please.
Thank you very much, Marcelo. Do you hear me? Do you see my screen?
Yes, perfectly.
Okay, very good. I will try to get a laser. Do you see my laser?
Yes.
Okay. Thank you very much, Marcelo, for the introduction. First of all, thanks for the invitation. It is a great pleasure to be with the Brazilians today, closing the meeting of the Brazilian Physical Society. It's a pity that I am not there to meet all of you personally. I would have enjoyed it very much. So my talk today is about quantum simulators, one of the most beautiful legacies from Feynman and one of the least known is the idea of constructing matter in a bottom-up approach. Nearly 60 years ago, in a very provocative talk, he told us there is plenty of room at the bottom. And with this sentence, he was inviting us as physicists to not only explain or try to understand how matter works, but to build matter in a way to serve our needs. So at the time, it was really a very avant-garde talk, and it took many, many years until people started realizing this kind of possibilities. Excuse me, I hear some noise. If it would be possible to shut down the micros. Okay, so the beginning of the field of quantum simulators happened with the optical lattices. People started crossing lasers to build something like an egg box of light, putting atoms there and simulating several kinds of models that we knew in condensed matter. This field has been already quite developed during the last 20 years at least, And in the last 10 years, more or less, also with photonic systems, people have been doing lots of progress to simulate states of matter. But in these fields, if you look at optical lattices, the entities are atoms. And in photonics, these are photons. And in a world where most of the equipments are based on electronics, you wonder, why didn't anyone try to do quantum simulators with electrons? Or have they tried? Where is the field at this point? That's what I'm going to tell you about, how to build quantum simulators with electrons. Well, the ingredients that we are going to use for our quantum simulators, there are three things. First of all, we'll use surface states in metals, like copper, for instance. Above a certain energy, there are certain surface states, Shockley states, where you have at the boundary of your system, you will have free electrons with a renormalized electron mass. Okay, so you have them floating around. Then we will use something which is called a scanning tunneling microscope, and we will use this in three different ways to construct the structure and to probe the structure. And then we will use some kind of adsorbates, adatoms, and our adatoms, we will use hundreds of them, not only 100, but 500, 400, depends on the system. And with the experiments I'm going to tell you today, we are going to use carbon monoxide, COs. Okay, a little bit more about the scanning tunneling microscope for the ones who don't know. So this is a microscope that ends up, as you can see here on the figure on the right, by a single atom. So it is a needle that is very, very thin that you will approach to the surface that you want to study, and you apply a voltage between the surface that you want to study and the tip, and you will be able to detect a current. So with this kind of scanning tunneling microscope, you can see the surface atom by atom. So it's a very nice probe to understand what is at your surface. But you can also do another thing. So you can operate in two ways, either at a constant height or at a constant current. And in one way, you will see the topography. So if you are at a constant current, you can see the topographic image of your structure with an atomic resolution. Or if you then, now you will change your voltage, and you will measure the variation of the current at a constant height. And with this, by seeing how the current changes as a function of the variation of the voltage, as a function of voltage, you can measure the local density of states. You will have electrons either tunneling from the sample to the tip if you are probing occupied states, or vice versa, from the tip to the sample if you are probing empty states. And you can get a view on the local density of states. So it is a very powerful instrument, and that is what has been used in 1993 in the group of Don Eigler at IBM. So if you look here at the first figure, you see the IBM letters spelled with 35 xenon atoms. So each of them is one atom that has been patterned very carefully on the surface to form the IBM word. On the right, you can see this beautiful movie. You can find it on YouTube. It's called A Boy and His Atom. So each of these white pixels is one atom, and they have been making the smallest movie ever made. This movie is made on a nanometer scale. Okay, the separation between two white pixels is in the nanometer scale. And the movie was made for the publicity of this beautiful work that was published in Science. So each of these yellow-orange spikes that you are seeing here is one atom of iron. So, and underneath the surface is copper, the copper 111 surface. So what this group did, they made a chorale, so a circle of iron atoms, okay? The separation is 1 nanometer, 1.1 nanometer. And then what happens is that this confines this electron gas or electron liquid, which is inside the quantum chorale, and you can see the electronic waves. Isn't it marvelous? We have a quantum chorale. So this was in 93, as you can see here, but it took very long time until people applied that afterwards to do a lattice. So let's understand what we can do with the technique and what they are seeing. This is very easy. If we take already when we are doing quantum mechanics 1, we learn how to solve the problem of a particle in a box. And then we can plot the modulus of the wave function square. And we know that we are going to have several kinds of solutions. Solutions that have only the nodes at the boundaries, which are like this, or solutions that have also one node in the center, or solutions that have 2 nodes. Here I am plotting them on the right. Now you can represent this 3D picture in a 2D map by saying that everything what is very high, you will paint in white, and everything what is very low energy, you will paint in black. And that's what you get down here. So this black and white contrast is just the projection of the previous figure. And these are exact solutions of a particle in a circular box. And if you look at the local density of states maps that you would measure with the STM, you would see the images which are on top. So even with this very rudimentary type of calculation, you can already capture the main features of the local density of states. Okay, so, but that was then for one chorale, right? Now I am showing you here how to build. The black ones are going to be carbon monoxide. I create a circle and I will get an atomic site here in blue, which will have a certain energy. What you are seeing in the underneath each of these orange dots are the copper atoms in the underlying copper lattice, okay? So what is very beautiful here is that if I increase the size of my chorale, if I make it slightly bigger, the energy of this bound state here, this energy state will come down. So I can control the energies where I want by controlling the size of my chorale. And I can also not probe only the lowest energy level, which has a S-like state, but I can go to higher energies when I am going to see P-like states, which now have the node in the center. So all this is for a single chorale. Now I can try to combine 2 of them to go and make some lattice. And what is very nice is that when I combine 2 here, and you see, I just have cut out 1 in the middle to allow for some tunneling. And then what happens is that because of the tunneling, my energy level will split and the energy separation is proportional to the tunneling amplitude. But I could make this tunneling a bit larger. So instead of confining with this black CO down here and letting this very narrow passage here for the electrons, I can make them more separated. And then these energy levels will be more separated in energy. So I have an experimental setup here that allows me to engineer the kind of lattices that I want. And this is very nice. So that is what has been first realized in the group of Hari Manoharan by a Brazilian, Kenjiro Gomes. He has a Japanese name, but he's Brazilian. He's now a professor in the US. And this was published in 2012. So what Hari Manoharan did, here you can see the yellow is copper, the copper surface with the electrons, and these brown dots are carbon monoxide molecules which have been absorbed on top of the copper surface. Wait, sorry, I have to get rid of my laser pen to be able to play the movie. And now what he does, he will take with the tip of the STM, he will pull these adsorbates, these adatoms, one by one to form a triangular lattice. And when they form a triangular lattice, they are like little mountains for the electrons, which are moving around. So the electrons going around a triangular lattice, they are going to form a honeycomb lattice. And this is extremely beautiful. And you can see here that with the honeycomb that has been created, so you have, if you look at this structure, and if you look at the same taken with STM for real graphene, you would see precisely the same if I don't tell you that this bar here is 2 nanometers. In graphene, it would be, the spacing would be of the order of angstroms, and here it's of the order of the nanometer. It's a 10 times larger graphene lattice made artificially by hand, with perfection, because if one atom is out of place, you will know it and you can repair, okay? So he could then, by looking at the density of states, he could also see the Dirac cone in this structure here. So that has been a marvelous experiment, and that's where the field was when we started working in that field. And there was one issue there, that Manohara has been patterning this triangular lattice because you can also only put the COs on top of the carbon atoms. And the copper 111 surface is triangular. So he was patterning a triangular lattice on top of a triangular symmetry substrate, which was very easy and possible to do. But the first question that we asked is, can we use this technique to make any kind of lattice, not necessarily a triangular lattice? And so that's the first work that we did. I now give you an outline of the talk and the things I'm going to show you. The first thing we did was to build a square lattice, which is a decorated Lib lattice. Afterwards, we went on and we tried to control the orbital degrees of freedom. After this, we tried to generate flat p-bands. You know that people are getting crazy with twisted bilayer graphene because you have flat bands. Here we are trying to engineer flat p-bands. And we went on trying to control topology by looking at the edge states in a Kekulé lattice, which is a topological crystalline insulator, and looking at higher order topological insulators, if we could create a state like this in a Kagome. And we tried also to control the dimension by creating a quantum fractal. So it looks very ambitious, but I hope that I can give you at least a taste of all the possibilities that we have with this technique. Okay, so the first work controlling the geometry, I would like to show you the main hero. It's Marie-Louise Lott, who was doing the experiments. She is a PhD student of Ingmar Zwart, who is the STM specialist in Utrecht. And Peter was doing also a bit of the tight binding calculations together with a student in my group. So usually we do the calculations and they do the experiments. Okay, so we decided, they came to my office, that's how everything started, and they asked me, what do you think we could build that would be interesting? And I immediately said, a Lib lattice. So I was always fascinated by the Lib lattice for several reasons, and I keep discovering why I was so fascinated. The first reason is, it is the true lattice of high TC cuprates. Everybody studied the cuprates looking only at the copper lattice, and they build a square lattice, which is the blue one. But actually, cuprates have this copper oxygen planes, copper O2, and you have these 4 red atoms here, which are the oxygen. So that is the true geometry of high TC cuprates. Another thing that makes this lattice so interesting is that if you look at its spectrum, E versus K, you will see that it has a Dirac cone, like in graphene, and it has also a flat band. So it has very interesting spectral properties. Flat bands are very nice because with the STM, what you will see is that you have a huge peak because you have infinite, theoretical and infinite density of states. So it will give you a large peak with many, many possibilities, many, many possible states, okay? And the V-shaped of the blue is the Dirac cone that I am seeing up here. And what is also very nice in this lattice is that it has 3 sides per unit cell. And these sides are inequivalent. So first of all, one has only 2 neighbors, the red sides. The blue sides have 4 neighbors. So I have sites with a different connectivity. It's an interesting lattice, different than the usual ones, right? And if I think in terms of pseudo-spin with the 3 atoms per unit cell, it would be pseudo-spin 1, which goes beyond the paradigm of graphene, which is pseudo-spin 1/2. Okay, so I liked this lattice for many different reasons. And I asked them, let's try to build that. And that's what they came about. So you put lots of COs around to make a box. That's the contour that is here. And there, since we wanted to prevent the electrons from going to the center, we made this cross here that looks like jogo da velha, right? And now we expect that the electrons are going to sit at the red and the blue positions, which are here around, and form a Lib lattice. So after you have built, and you do a topographic image to see if you have built everything correctly, you now sit at one position, let's say at one red. In reality, you sit at many red positions and take many spectra to average. And now you vary the voltage and you see how is the current changing as you change the voltage, okay? And if you sit in the red position, you get this red spectrum here. If you sit in the blue position, you will see that one. So you can see here that if you do calculations like tight binding calculations, we are going to have this kind of answer. So you see the blue one, it's of course not perfect because this is real life, these are experiments, looks like the V shape of the Dirac cone. And this big red peak is the high density of states that you have due to the flat band. Our band is not perfectly flat because we have next neighbor hopping, which is very important, and this bends your flat band. But we could look then, we could sit at certain energies at all the sample, and we could understand the density of states in this sample to perfection. So the technique works. That's what we have learned from there. The kind of calculations that we were doing, it was 2 kinds of calculations. One is you use what is called the Muffin Tin Model. So here you have the tin, and you put a tin to bake muffins inverted inside, and your electrons are going to move here in between these mountains. So the mountains are representing the carbon monoxide molecules, and the electrons are moving around. And you can now solve a Schrödinger equation in this type of potential that you are creating. This would be a square lattice. The other thing that you do is you want to know whether your finite size structure is reproducing features from an infinite lattice. So then you solve a tight binding model in an infinite lattice, and you try to understand which should be the hopping parameters such that your Muffin Tin model can be adjusted to fit the energy bands in the tight binding approach, okay? So these calculations are relatively simple. The kind of work that we are doing, which I consider the most important, is the conceptual work. We try to find out what kind of system it would be interesting to create. How do we create? Because you can have your surface states only in a certain range of energies. So you have to do all the calculations to get the features to be discernible within the energy range that is accessible experimentally. So that's the art which is behind what we are doing. So the next work that we did is still with the Lib lattice. It was a trial to control the internal degrees of freedom of our lattice. And again, Marlou was doing the experiments, and Sander Kempkes, who is a shared first author with Marlou, who was my PhD student, he just graduated, he was doing the calculations. Okay, so you see, if you do the measurements at minus 50 MeV, you would see these S-like structures that I have been showing you before. So you would see these white structures here. But if you come to 550 MeV, you would see that the structure changes quite a lot. These are the peaks and the bottom of these structures that I'm projecting in black and white, as I have shown you before. And the scale bar is 5 nanometers, okay? So this is because when I am here around 0 at minus 50 MeV, I am probing the S bands of the Lib lattice. I have 3 bands because remember, I have 3 sites per unit cell. But when I come here to 500 MeVs, I'm in the blue region of the PX and PY bands, okay? And indeed, you can see from the theoretical predictions with the Muffin Tin, if now before where I had the high intensities, it's where I have the green here. It's where I have black spots now. I am painting them green just to show you that this is the center of these PX-PY orbitals, okay? And you can see now I have nodes down there and the high intensities in between because I have PX-PY bands. And what you are seeing here on the left side are the experiments. So our theoretical predictions fit very well. And we have PX and PY, and they are both degenerate. But now in energy. Now I would like to control these lattices. I want to decide which orbital I am going to put in which position. So to do this, I have to change the lattice that I have been constructing. And we will now, instead of having the 5 COs that we had here in the central part, we are going to put 12, 4, 4, and 4. Actually, we should have put 14. We should have put 1 more here and here because these are spurious things that I don't want. Okay, if I would redo this experiment today, I would get 1 more CO here and 1 more here. But at that time, we still didn't know that. So, and now what you will be able to observe is that around here in my lattice, at this site, I get only PX. The PY has been pushed away in energy. At the corner, I get PX and PY, and here up, I get only PY. And these are the experiments, and this is the theory indicating that indeed, we could control by design which orbital goes to which lattice site. But there was a problem because the energies of PX and PY were still degenerate. So I also want to control them in the energy range. And now we know which is the symmetry protecting them, this degeneracy. And what I have to do is just to break the C4V symmetry of the lattice. So instead of building everything on top of a square lattice, I build it on top of a rectangular lattice. And when I do this, I immediately split because the energies, because now at plus 50 MeV, I get only PX in my lattice. This is experiments to the Lattice theory. And at plus 50 MeV, I get only PY. So this would be analogous to the experiment made by Zeeman. You remember the Zeeman effect. You have the spin up and the spin down, which are internal degrees of freedom of my electron, which are degenerate. And when Zeeman applied a perpendicular magnetic field to the sample, he could split these energy levels, right? The magnetic field lifts the spin degeneracy. For us, breaking the lattice symmetry lifts the orbital degeneracy, okay? And then I can separate PX from PY. Okay, so we could control orbital degrees of freedom. Then we thought, okay, it would be nice to play a little further and to generate flat P bands, because these people didn't do it with graphene. They are all playing with the S kind of bands. And this is a work that was just published. The 2 main authors are Thomas Gardenier and Jette van den Broeke, who is a PhD student in my group. And Danielle van Mackelberg is the experimentalist who was leading this experiment. Okay, so what we realized is the following. Here are the black COs on the left in the image A, and these gray drawings here are the positions in the honeycomb lattice that the electrons are going to occupy. And this is precisely the lattice built by Manoharan. And this lattice has the Dirac cone that you see here underneath at the K point. And if you would look at the local density of states, you would see this V shape here where the arrow is marking in the underneath figure. What we realized is if instead of putting one single CO, we make a rosette with 6 COs per barrier. Instead of one barrier, I make an ensemble of barriers. So we calculated, Yete calculated, what do you get for the band structure of this system? And you see, you start getting a yellow flat band in the system. So you get your Dirac cone at the K point here, and you start getting a flat band. And the flat band will be visible here by this arrow that you see that there is a peak. That's a large peak. And you start getting also a Dirac cone at the K point, but it's a P Dirac cone that it's being indicated by the next yellow arrow. But the P bands and the S bands are still all connected in this configuration. So what Yete went on calculating is what happens if now you do a rosette with 2 layers of COs, a much bigger mountain of rosettes. And now look at what happens. Now you separate S from P bands, and your P band gets very flat. Look what a beautiful feature. She was telling them that they should try to measure this very huge peak. And it was a challenge to build experimentally, but she can tell them precisely where you have to put each of these COs. That's the advantage of doing the design before building. You know what you are looking for, you know what you will achieve with that type of construction, and you know precisely where to put each atom. And then that's what they could measure experimentally. So in green here, you see the S-type Dirac cone. Here in violet, you see the P flat band. And then here, 5, 6, 7, you see the P Dirac cone. So on top of it, you are seeing the positions at the green and the violet when you are measuring, doing spectroscopy. And underneath in the continuous here and shaded, you will see the theoretical predictions. Everything agrees very well. So we have a way to create flat P bands. Okay, after that, we have been controlling the geometry, the orbital degrees of freedom, flat P bands. We thought, what else could be nice to do here? And the answer was topology. And what we tried to do is to build what's called a hottie. And I will tell you in a minute what this is. The main heroes of this game are Sander Kempkes, Jette van den Broeke, so the 2 of them for the theory, and Marlouis Lott for the experiment. So, topological insulators. If you never heard about this, what is that? This is a fascinating state of matter which is simultaneously insulating and metallic. So it is a material that is insulating in the bulk, but it's metallic at the edges. And this these currents which are running at the boundaries, they are, first of all, quantized and they are protected. So they are very robust. It's very difficult to destroy them because they are protected by what is called a topological invariant, which is a number that tells me how many modes are carrying currents at the boundary. And it is something that emerges independently of all the details of your material. It just depends on symmetries, okay? If you know the dimensionality and you know symmetries which are preserved or broken, you can already make the predictions about the nature of these edge states. So usually if you would have a 2-dimensional system, it is insulating here in the 2-dimensional bulk, but in black you would have these edge modes which are running around. So these are the usual topological insulators. And then what would happen is that if you would look at your energy versus momentum graph, you would have the bulk bands, which are in light blue here. And then you have a gap because it's an insulator. But inside this gap, you will have states which are connected to the states that are running at the edges, okay? So this light blue refers to the bulk, and these dark states here in the middle that are crossing, they refer to the edge. And usually in these topological insulators, which are driven by spin-orbit coupling, they are crossing because spin up propagates to the right and spin down propagates to the left. And that's why you see this feature It's referring to the two types of spins of your electrons. But there is another kind of topological insulators, the so-called Lattice, which means a higher order. And this occurs when now the bulk, which is insulating, and the topological states have at least 2 dimensions less than the bulk. So this one had just 1 dimension less. The bulk was 2D, the edges were 1D. This one has to have at least 2 dimensions less. And it means if I am in 2 dimensions, the only possibility is to have corner modes, which are 0-dimensional. And here you see the 0-dimensional corner mode. It's localized, it cannot move, it's just a dot. Okay, so usually these Lattice, they are generated in quadrupolar systems, but here we are trying to do something which is not really a Lattice in the most strict sense of the word. It would be just what we are trying to create are 0 modes at the corner of our structure. And there were predictions that you could realize this in a breathing Kagome lattice. So what is a Kagome lattice? The Kagome lattice is the lattice that we have in all these baskets. It's the most common lattice that we have in baskets. It is a honeycomb, and then you have these triangles in between. So you get triangles looking down and triangles looking up. The blue are looking down and the pink are looking up. And now we are going to make these triangles, these bonds between the sides, weak and strong, as we do in a Sushriff-Higger model. Okay, so we'll have 2 types of hopping. That's why it's called a breathing Kagome. And if TA, which is the pink, is 0, I would have just these disconnected sites at the corner and these dimers or these trimers in the center. And if it is smaller, I connect them here by a weak site. And if this becomes very strong, I will have a trimers, just a lattice of trimers. So there was a prediction by Yazawa that in this lattice, we should be able to see a higher order TI. And that's then what we have been building, and we have been making the design for that. You see, we are going to have corner sites which are in blue, edges which are in yellow, and bulk which are in green. And this is now the 2 designs that we have made in C and in E here. So what distinguishes them is the number of COs, which are these black spots surrounded by the green circles to make you see them a bit better. And you will see that here, to have a non-trivial lattice, I have to have these last 3 hoppings here close to the corner to be weak. And to make them weak, what I do is I put lots of COs here, and then the hopping there is going to be weak between this and this, and to be weak also there. I approach them there, okay? And then I can also build the same lattice, but now just with 1 CO here. And now these hoppings, all the 3 are going to be strong. So the amount of COs that I am going to put here in the center decide whether these 3 hoppings are going to be weak or strong. And after I have built the lattice with these characteristics, I can now sit at the different sites and take vary the voltage and measure the GIGVs. And you will see that if I am sitting in the green, I am going to see two, you see there is a bump here and another bump here, that as you see here in the theory. In the yellow, there is a bump and another bump, as you see in the theory. And in blue, there is a peak, which is in the theory, it's more pronounced because of course you have a broadening. These states, they scatter with the bulk and they are not infinitely sharp peaks, but they have a certain broadening. But you can clearly see the difference with this one sitting at the tip of the yellow and the green. And if you have a trivial lattice, no matter if you are in the blue, the green, or the yellow sites, at the corner, at the bulk, or at the edge, all the spectra are precisely the same. So it is this blue compared to this one that shows that I have a 0 mode here. And now it's quite nice because after I do this, I know now at which energies I should do the scan of the entire lattice to see these features. And now you go to minus 110 MeV, 5 MeV, and 50 MeV. And you will see, let's start with the trivial lattice. You will see that all these energies everywhere in the bulk, boundary, and corner, everything is the same. But for the non-trivial lattice, you see that the red parts, which are the high energies, are in the bulk. Here they are around at the edges, and here they are at the corner. And here in the theory, we have just much more pronounced effects from the bulk to the edge to the corner. So we have corner modes that have been created in these gaps. Then what we have been doing is we have been introducing defects in our structure to see how robust these corner modes are. And you can see that here, for instance, these are the corners. I have been destroying the right corner mode, but the up and the down remained. And now we have broken the symmetries further by adding a protrusion here with 120 degrees defect, and my 3 zero modes remained. And when now I have added a protrusion with a 60 degrees defect, I can add one more zero mode. So I can manipulate the zero modes, which are these corner modes, at will. I know how to destroy them or how to engineer them by adding protrusions. So that was a very nice control of the zero modes in this higher order kind of topological insulator. So the next time we wanted to control, we thought, let's now try to understand the effect of the boundaries. And again, I have Sarsha doing the experiments in the group of Ingemar Zwart and E.T. van den Broeke doing the theory. We went for another kind of topological insulator, which are now the topological crystalline insulators. What is that? It looks like the honeycomb lattice again, but now, like the breathing Kagome, I will have two types of hopping. So I will have one type of hopping inside the honeycomb and another kind of hopping connecting one hexagon to the next hexagons, T0, T1. Okay, so this structure is called a Kekule lattice. And again, there were predictions for these Kekules that the type of termination in this lattice is very important for the topology. And for that, we are going to investigate different types of termination. Something what is called a molecular zigzag that I am showing you here on the left. Something that's called a partially bearded, so it's like an Italian beard. They didn't cut the beard completely, just half. And also an armature, but I will not show you the results for the armature, just for these two because they are more interesting. And the choice of edges here is to avoid break sublattice symmetry, because if I do just a normal zigzag, I will terminate with only one sublattice, only A or only B for graphene, and I don't want. I want to have both A and B sublattices in my termination. That's why we have these two special lattices. And there was a beautiful prediction by Cariado in the group of Xiaohu that if you build a certain lattice, depending on the termination, you will have that one lattice is topological, the same lattice with one termination is topological, with the other it's not. And if you invert now who is stronger, T0 or T1, the topology inverts for the terminations. The one which was topological now is no longer topological, and it becomes topological for the other termination. So now to verify that, we need to build 4 lattices, right? So, and that's what we are going to build here. This means we are manipulating 500 COs. More than 500, 534. And so the green ones here are copper, the blacks are the COs. We manipulate this hopping. You see here, the T0 is going to be large because this is open and there is only one here. But now I put 6 in the center and I close, I put the open to the other side. So now here T0 is small, the red is small because this structure is very confined. So by arranging the positions of these black COs, I will control the hopping. And then you have to control also the termination without adding spurious additional crystalline potentials. You have to do lots of calculations to get this turning right. And those are the terminations for the 4 lattices. This was a tour de force to build all that. And now you can see the results are quite nice. So if you have T0 larger than T1, the honeycomb is strong. You see the honeycomb is very strong and the connections are weak. And you terminate by a molecular zigzag. These are experiments here. Underneath you get the theory. All sites, you can sit in all of them, you get the same results in the measurements and in the theory. But if you have a partially bearded one, the red ones have a peak, and the violet also have a peak. The blue and the black have a dip because they are insulating, and these are your edge states, okay? If you now, you can see them visibly, it's very nice. The whites are your edge modes. They are here, they're not here. And these are our calculations with the tight binding, the topological on the left and the trivial on the right. And you see that I had a strongly connected honeycomb, hexagon, connected by weak links. Now I change. Now I make weak hexagons connected by strong links. Now the left one becomes trivial and the right one becomes topological. You can see now that the blue and the yellow became high in energy, they became topological, and you have the dip in the black, and the green has also a dip, but it's a quite high dip there. And now you can see that this state now is topological and the other became trivial. So it's the combination of the type of which bond is strong and the type of termination that determines the topology. This is much more complicated than in usual topological systems driven by magnetic field or by spin orbit coupling, in which the termination of the sample is irrelevant, okay? Now, in these topological crystalline insulators, the termination of the sample defines the unit cell and decides who is topological or not. Okay. So I can't see the time here. I hope I still have some time to tell you our last work that I want to tell you today, which is the last question we were asking about dimensionality. And we wanted to understand how electrons behave in fractal dimensions. And we wanted to control the dimensionality. And this is, in my opinion, the most interesting of all the works. The heroes are again Sandra Kampkes, my PhD student, and Marlois Lott. Okay, so what is this about? This is about fractals, and fractals are these beautiful structures that have most of the time the property of self-similarity. As I zoom in, I keep seeing the same structure over and over again. So on top here you have the Koch curve, which appears in the snowflake. On the right, the Mandelbrot set, and down here, what is called a Sierpinski carpet. It is a square that I have divided into 9 squares, and I have cut the center one. Then I took each of the remaining 8 squares, I divided them into 9 again, and I cut the center one, and I do like this successively. And as I keep zooming in, I see always the same structure. So, a fascinating thing about fractals is that they have a fractal dimension, which is a non-integer dimension most of the time. What does this mean? So the dimensionality is given by a formula which is called the Hausdorff dimension. And the Hausdorff dimension is given by the log of the number divided by the log of the scaling. What does this mean? Suppose that I have a red line. Now I apply a scaling 2. So I made this line twice as long. That is the 2 which is here on the left-hand side. Now you ask yourself, how many of the original red ones I can fit inside the black one? 1, 2. That is the 2 which is on the right-hand side, because the dimensionality is 1. If I take the red square here on the top, and I scale it by 2 in the X direction and by 2 in the Y direction, I get the scaling 2 here. And I ask how many of the original red ones I can fit inside. 1, 2, 3, 4. That's the number 4, which is here because the dimensionality is 2, log 4 over log 2. Now take a red square, a red triangle, paint it completely red. Paint this one completely blue. Now scale the red triangle by 2 in this direction and scale the red triangle by 2 in this direction. I get these 2 here. Now ask yourself how many of these completely red triangles I can use to cover this entire surface. 1, 2, 3, 4. The inverted one is another one that I could use to cover. And I would get 4. I would be in two dimensions. But if I have a Sierpinski fractal, a Sierpinski triangle is a triangle in which I have cut down the inner part of it. And then I had 3 remaining triangles of which I also cut down the inner part. So it has lots of voids. And if I have a Sierpinski triangle and I look to the right now, how many I have of the original red ones? 1, 2, 3 only. I get 3, and log 3 over log 2 gives me 1.58. So that is the dimensionality of the Sierpinski carpet, gasket, sorry, the carpet is 189. Okay, so this Sierpinski fractal is something that is absolutely nice, right? And fractals are not just these geometric mathematical ones that I have been showing you there. Fractals are pervasive in our daily life. If I go to the supermarket and I buy Romanesco broccoli, it is a fractal. If I look at the branches of the trees, it is a fractal. The roots of the trees, it is a fractal, and it's very important. The fractality of the roots prevents earthquakes. If I look at the ferns, the leaves, they are clear fractals. Fractals are not only in nature, they are also in our human body. Our lungs are fractal. Our neuronal system is fractal. And we don't have only spatial fractals in our body, we have also dynamical fractals. Our heartbeat is fractal. And if it turns out to be completely periodic or perfectly chaotic, you are ill, seriously ill. It has to be fractal for you to be healthy. So fractals are also extremely important for science. So look here, there is this very old telephone with a Sierpinski fractal antenna. But what is very nice with this antenna is that because you have large and small length scales, you can send and receive simultaneously large and short frequencies. So they are very rich. Here on the right, you can see solar cells, which are covered with fractals. This light blue, this blue here on the right is telling me that as I increase the complexity of my fractals, I can store more and more energy on the same surface of my solar cell. So it's nice, I can do lots of stuff in technology with these fractals. And fractals are also very important in arts. For instance, these are a tiling decorated in a church from the 11th century before Christ, when mathematicians didn't know much about fractals. Or we have this beautiful painting by Escher, where he goes into the boundaries and gets the structure getting smaller and smaller. Or Pollock, who has been pouring colors by high, and depending on the density of the colors, he would form structures with different fractalities. Okay, so these are fractals with the different fractal dimensions, and his fractal dimensions has been increasing with age as he said he has been growing older. Okay, so we decided we would love to build a quantum fractal of electrons. So for this, we wanted to build a first, a second, and a third generation fractals. On the right, you see the COs that we are putting here. And down here are the models that we are going to have for the first generation in terms of a tight binding T and T prime. And on the right, you get these atomic sites in red, blue, and green. I painted them with different colors because they have a different number of neighbors. Red has just one neighbor, blue has 3, and green has 2. Okay? So now we are going to sit at the red side and take the GIGV as before in the green and in the blue, and we get all what you are seeing here. And this tells me I can do a tight binding calculation and reproduce the main features. And now when I look here at these experiments, I see there are 3 voltages that are interesting. One here at minus 325, around minus 300 milli-electron volts, when red, blue, and green are equal. Here, when red is down, green and blue are high. Here, when blue is down, red and green are high. So now we are going to sit at these 3 energies and scan the entire sample. On top, you see the experiments. At the bottom, you see the theory. They agree very well. The vertical, first vertical is minus 300 MeV. The middle one is minus 200. The last one is minus 100 MeV. The first configuration is a bonding. This one, you start partitioning the structure, and here it's an anti-bonding configuration. You can see this structure in 3 dimensions. This is the theory on top and the experiments underneath. We have built a Sierpinski fractal. But now the question is, do the electrons know that they are living in a Sierpinski fractal? Do they know that they are living in a fractal dimension? That's what we wanted to check. And to do this, you use a technique that's called Minkowski-Bulligant or box counting. And it consists of, first of all, projecting the peaks into black and white, and you get the figure which is here. We are at minus 300 MeV. And now, what the technique tells you to do to find out the dimensionality is to choose a certain radius for a circle or for a box, a length of a box that is small or reasonable compared to the size of the structure that you want to cover. And now you cover this structure with many of the circles. And then you count how many, 1, 2, 3, 4, 5 you need. And you plot the log of the number versus the log of the inverse radius. And you will get 1 dot for this size of circle. Now you change the size of your circle, you make it slightly smaller. And you fill everything, you cover everything again, and you count again, and you will get another dot. And you do it again for a smaller one, for a smaller and smaller and smaller. You do many, many times. And then you start increasing the size of your circles, and you cover again, and you count again, and you will get lots of dots. And these dots will sit on a straight line. And the slope of your straight line is the dimensionality of your object. That's the prescription for the box counting method. And when we do this here, we get 1.59 for a mathematical structure that has dimensionality 158. So it looks quite good. So we do this not only for minus 300 MeV, but we do it for many, many energies. And as you can see here, now there is an error bar. And the error bar comes because when you look at this picture, you look here, this is gray. It's not white, it's not black. The question is, should I cover it or not? I have to get a binary structure, which is fully white and fully black before I cover. And I have to take a decision about what gray is white or black. So you have to take certain, well, this is ad hoc. You say, okay, I will consider that everything which is above 65% of the highest peak, I will call white. But you could have taken 55 or 75. And this will give you the error bars around this 65. But in any case, you are around 1.6, which is very different than 2, which is the dimensionality that you have if you have a graphene lattice or a square lattice. Okay, so we could show that the wave function has a fractal dimension. We did the calculations also for first and second generation. So everything what I told you until now, it was with the STM. But I want to show you 2 slides because STM can only probe the static features. If you want to study dynamics, you can't do it with the STM. And now we would like to study how is quantum transport in fractals. We would like to study that. And we then started looking at that with the group of Professor Xiaoming Jin in China. And the main student who was behind the experiments was Xiaoyun Chu. This paper is not yet published, is under review. And that's basically the problem of a quantum ant in the labyrinth. So Dejean was studying classical diffusion and saying that that's the problem of an ant in a labyrinth, but now the ant became quantum. And basically, the structure we are doing is now using photonics. You have several waveguides, and the cross-section of these waveguides is forming a Sierpinski triangle. And now you will make many, many hundreds of these sets with different lengths here in the z-axis. And this measures the time, because since the light's propagating with the speed of light, after you detect them at a certain length, you know the time that they have been propagating. And now you inject light on top and you see how it spreads by quantum tunneling. If you would have this is for on top here, you have for a normal triangle. And now here you see we are injecting on top of the Sierpinski triangle. And you will see that when the light meets the first hole down here, it starts going around, and we can now detect the variance, so the mean square displacement, as a function of the propagation length in the perpendicular direction, which is like time. And what is marvelous to see is the following. It starts propagating with a certain exponent, which is the same as if you would have a continuous triangle. And when it meets, you see at 2.675, you can see the light has met the hole. And at that point, the exponent starts changing. The photons start going around and looking for a way to go on propagating. And when they are here, they can go on propagating again. And at 3.5, they are coming at the boundaries there. At 3.875, I show you in the next slide, they found that they can go on. They understood this is a Sierpinski gasket. And then they start propagating with an exponent, which is precisely 158. So these photons are damned smart. And afterwards, when you come to the boundary down here, it saturates. This holds for several kinds of other fractals. We investigated all of them. There were 3 different ones with the different fractal dimensions, but it's amazing to see. It knows precisely when it reaches the point that it has gone around here, and then it picks up the fractal exponent. I find this very impressive. So I came to the end of my talk. I just want to let you with an inspiration that inspires me very much. So our friend Einstein has been telling us that God does not play dice with the universe. And I want to ask a question. Is this indeed the case? I am not so sure. Let me show you why. We are going to play, the game is also in YouTube, and it's called the Quantum Chaos game, okay? We are going to draw a triangle, and the triangle has 3 vertices, and we are going to play dice, but I only know dice with the 6 numbers. So for this reason, we are going to call the upper corner 1 and 4, the second corner 2 and 5, and the third corner 3 and 6. So 1, 2, 3, 4, 5, 6. And I play dice. I will choose a random point inside a triangle. Every time I get a number playing dice, I will connect that point to that corner that is numbered. My corners are numbered. And I will pick up the middle point. And I will see which structure I get. You will see again a repetition of what I said into this video. A random point inside the triangle, play dice. You got a number, let's say 2. You connect and you choose the middle point. Play dice again. You got 1. Connect and pick up middle point. and you go on playing dice, and you get lots of random points. And if you are patient enough, you are going to get a wonderful Sierpinski triangle after many thousand iterations. So if we see that nature is fractal, the human body is fractal, and we can create fractals out of a chaotic game by playing dice, I am not so sure anymore that God doesn't play dice with the universe. Okay, with this, I would just like to tell you my outlook with my wish list. Everything what I told you today is no interacting physics, okay? So we need now to reach the strongly interacting regime, and we'll have to do this using gating or using different substrates, maybe using semiconductors with different kinds of patterning. We could try to engineer the surfaces of 3D topological insulators. These are Dirac electrons. It would be very interesting. We are now studying substrates with a strong spin orbit coupling to generate topological states of matter which are intrinsic. We would like to engineer strongly correlated phases in flat bands, if possible, in flat p bands that we have shown that one can create. And I would like to understand more the topology in fractal dimensions. And one of the things that this work has motivated us is to start learning about fractional calculus. So that is something that we have been doing recently. It is on archive. And this was a master student that has been co-supervised by Rodrigo Ozella from the University of Belém, who has been visiting my group. And we have been seeing that it would be possible to create a time glass by investigating the fractional Langevin equation. Okay, I can't tell you more about that. It was just to let you curious. Maybe you will check the paper on archive. Let me just conclude my talk by telling you that we have been experimentally building a Libby lattice and controlling the orbital SPXPY degrees of freedom. With this, we also learned how to generate a flat p-band and p-Dirac cones in artificial graphene by creating rosettes of atoms. We have then afterwards designed and built an electronic hotchie to have zero modes engineered at the corners, and we could control at will the zero modes in the Kagome lattice. We also have been studying how the appearance of topological states at the edges depend or not, they depend on the type of lattice that you have and on the termination of your sample if you have topological crystalline insulators. And I have been showing you that we have built experimentally a Sierpinski fractal, and now more recently by injecting photons in a photonic Sierpinski gasket built with waveguides, we could follow the behavior of the photons and understand when they realize that they are in a fractal and they start undergoing a quantum diffusion with a fractal exponent. We could see the quantum dynamics with unprecedented detail. And with this, I would like to conclude by telling you that there is plenty of room at the bottom indeed, but even more in a fractal. And I would like to thank you very much for your attention.
Thank you very much, Professor, for your talk. I think you can move on to some questions. Let me ask you if someone has some question. We have some in the chat.
Okay, so I could
let's see, I can read for you.
Yes, please.
Yes, please. I can read. Please stop sharing while I'm reading here. So okay. Yuri Ferreira told us, hello, thank you for your presentation. I'm very pleased to watch it. I just have a question. The control of temperature is a crucial part of your experiment. If so, what is the temperature that you use to maintain the coherence of the lattice?
Yes, thank you very much. Yes, so we are at 4 Kelvin. Yes, it's low temperatures, but there are very few experimental setups that could go to millikelvin. There is someone in Germany who has been developing a millikelvin STM, but it would not help us too much, because the main problem that we have here that is giving this broadening to our peaks is the scattering with the bulk. It is not the temperature that is limiting our resolution with our peak. It's the scattering. And for this, we would just need to use different platforms. Indium arsenide could be one that has very narrow peaks. We are currently looking into it. So we have to go to helium temperatures, but we don't need to go much below that. That's enough. Thank you for the question.
Thank you. Please, Eduardo, please, Granado. Go ahead. Granado raises his hand.
Yes,
Okay.
I just want to congratulate you, Cristiano, for this wonderful presentation. We are very, I'm a big fan of your work, and you know, just like to, in behalf of the organization of this event, to thank you very much for being here and sharing this with us. Thank you very much.
Thank you, Eduardo. Very kind. Thank you.
Thank you. Someone else? I have a question.
Yes,
I don't know if it's
Marcel.
silly or not. In your waveguide, the Sierpinski waveguide, did you try to shine in more than one spot to see if there is some kind of interaction?
Yes. So it is the following. If you shine, maybe the last figure is better to show, that one. So if you would have a triangle, and if you would, a complete triangle, and if you would shine light in the center, the diffusion would be just 2. It would be ballistic motion. This is what you would expect, and this is what you get. If you now start for a complete triangle, but you inject at the top, the system sees the boundaries, and then it's not a perfect ballistic diffusion, but it is with an exponent 2.5. This is a feature of the triangle. In the square is 2.4. Okay? Mm-hmm. This is the beginning. And then, so 2.5, because you are seeing the finite size of the triangle. And then when it meets the hole, it enters into the 158. If it would be meeting the hole from the very beginning, as it does in a dual Sierpinski carpet, I don't have the image here, unfortunately, it would start immediately with the fractal dimension. So the idea behind that is, if you would inject in the center of a regular structure, you would see ballistic diffusion with exponent 2. If you inject at the edges of a regular structure, you will have different coefficients of order 2 point something, depending if it's a square or a rectangle. And then this will change immediately in the moment when you start meeting the voids of your fractal. At that point, it stays in the limbo here until the moment when it has explored around it. You can see between this image and this image, immediately when it knows the size of this inner hole here, it starts picking up this exponent 158. And this is an experimental data, and underneath it's a numerical simulation. So you can see here dynamically how it goes.
Okay, thank you.
You are very welcome.
Somewhere else? If someone has some question, please open the microphone.
Please just ask whatever. There are no stupid questions. And the ones that you are hesitating to ask are going to be the most difficult ones, I am sure.
So,
hello, Cristiane.
Hello.
I have one question, and thank you for the nice talk. Very interesting. I'm really curious about one thing in the last part of your talk. When you're explaining to us the rules of the quantum chaos game, I'm really intrigued about, is there any particular reason to choose the middle point after you play the dice, or can we get a fractal pattern if I choose for, let's say, 1/3 distance?
Oh, I don't know.
Or
I don't know. I don't know. What I know is that if you would, you can go to the website. There will be lots of things there. If you type quantum chaos game in YouTube, you are going to watch wonderful things. It's what I do when I am confined. So, for instance, if you go for a square and you play the same game, you don't get a fractal. You will fill up the entire square. For the square, what you have now to get some fractal structure is that if you get twice the same vertex in a row, you cannot pick it up. So it depends, the game depends on the geometric figure that you have, and you will need different conditions depending on the different geometries. So for the triangle, you get it for the half. For the square, you get it if you take the half, but if you get twice the same vertex, you don't go the second time, you only count it once. And then you can build again a fractal. Otherwise, you fill up the entire space. I don't know what is the mathematical reasoning behind, but what I find fascinating is to get such a regular structure emerging out of dice, right?
Okay, thank you for your
You are very welcome.
answer. And there is another question in the chat.
Yes.
If someone.
Yes, I see here. Ana Teresa don't want to open the microphone. She written here in Portuguese.
Please go ahead.
Yeah,
Everyone can ask in Portuguese too, and I can also answer in Portuguese if you want.
Ana Teresa escreveu: parabéns pela palestra. Gostaria de saber se existe alguma diferença, se a ordem das faces dos dados são mudas nos vértices, por exemplo, mudando o sentido das faces 3, 4 e 6. Os resultados dependem das condições iniciais?
Eu acho que não. Porque tudo que você precisa é pegar um vértice ou outro vértice aleatoriamente. Tá? O game eu poderia estar jogando esse game com um dado de 3 faces. Só que eu não sei como fazer um dado de 3 faces, por isso que eu falo 1, 2, 3, 4, 5, 6. Não, você simplesmente tem que ir para os 3 vértices de uma forma aleatória, não importa como. Você podia chamar o 5 de 4 e o 4 de 5. Não faria diferença. Só tem que ser aleatório.
Okay, thank you.
Obrigada.
Someone else?
I have just one more question.
Yes.
Why do you use copper and iron, and why do you use carbon?
Yeah, okay. So what can you use? First of all, for the 2-dimensional electron gas, you would use the surface state of a metal. Copper is one of them. Could be gold, could be silver, right? Okay. So for the substrate, it has to be a surface state. The surface state of copper is above -400 millielectron volts. And this is something you take into account when you design your structure. And now, what do you use as a datum? So the first one, he used iron, right? And then Manoharan decided to use carbon monoxide. So the question is, there is not one recipe. You can use many different things. For instance, there are certain atoms that when you put them, they will immediately self-organize and form a lattice. So those ones you don't want, because even if you pull them with the tip of the STM to go to a certain position, they will come back to where they were before, because they self-organize, they self-arrange, okay? Then there are others that when they adsorb to the surface, they glue so strongly to the surface that you cannot push it. You break your tip of your STM, you break your needle, and you can't push it to move away. This is also not good. So you have, and this is chemistry now, you have to find some adatoms that they adsorbate, they will attach to the surface a bit, enough that when you move them to a place, they stay where you put them, but not too much, because you still want to be able to move them. And there are a few possibilities, and then you have to start playing with them to find out which are the good ones. Some of them, we have been playing also with the bismuth copper, for instance. You can have different things. We are now playing with heavier ones because we would like to have strong spin orbit coupling. And then there are several possibilities. Bismuth is very heavy, so bismuth is a nice material to start playing with. And you could imagine having adatoms which have a strong spin orbit coupling, and they give it to the electrons when they scatter against the barriers, right? Or you could imagine having a surface that has electrons with a strong spin orbit coupling also. So all that could be possible. And maybe there are others which are even better than carbon monoxide. Or we have been working a lot with the carbon monoxide because we already knew all the features. You know the band mass, you know the height, you know the diameter. And depending on the amount of those, you will have different broadenings from 40 MeV to 80 MeV. So this system is very well characterized. We started now playing with copper bismuth, and the bands are inverted, and you have Rashba spin orbit coupling. You have to start the theory all over. It takes a while until you develop a knowledge of the other system. That's also why we have been playing with this one.
Okay, thank you very much.
Thanks for the question.
Okay, I think we have to move to the closing section, but I will make one question from the chat and let the Fernando ask another last question because he's raising his hand here. Leandro Rizzi asking, have you considered to build up quasi-crystalline tiling?
Oh, okay. So quasi-crystals, quasi-crystalline what?
Tiling, I mean.
Tiling, yes, tiling, yes. So we have a paper that appeared yesterday on arXiv on a quasi-crystal. So quasi-crystals are these beautiful structures that usually emerge from projection of a higher dimension into a lower dimension. They appear as if they would have no order, but actually they have embedded into them the order of the higher dimension. So quasi-crystals and fractals are very different things, but it turns out that quasi-crystals might have a fractal in their hidden in the structure of their wave function. So what we show in this paper that appeared yesterday, Anwar Mustaj, with Sander Kempkes and myself, is you take a Fibonacci chain. So a Fibonacci chain, you start from a grid in 2 dimensions, and now you start from one vertex, and you draw a line with a slope which is the inverse of the golden ratio, okay? So this line is incommensurate. It's not going to cross any other vertex. So now what you do is you take a certain interval and you project all the vertices in this interval around this line into the line. And it will turn out that the separation is going to follow a Fibonacci sequence, which is a one-dimensional quasi-crystal, which is connected to the Andre Aubry-Harper model for the ones who know about that. Okay, so now if you project also, so what will happen is that in this Fibonacci chain, you have long and short bonds. So it's like my Kekule lattice that has 2 hoppings, T0 and T1. But these hoppings are now not like in the SSH like strong, weak periodically, but you will have weak, strong, weak, strong, etc., following a Fibonacci sequence. Okay, if you now reorder this lattice, this one-dimensional chain, according to something that's called co-number, and the co-numbers are obtained by projecting the lattice sites in a perpendicular direction, okay? So it's like knowing that it's originating from a two-dimensional structure. If you do this, you will see that the modulus of the, so the amplitude of your wave function square, modulus of psi square, follows a fractal structure. And this is extremely beautiful to see how the fractal emerges in the Hilbert space of these quasi-crystals. And what we have been investigating in that work was to build, to put disorder and to see how disorder is going to follow a certain structure that can be predicted by RG. And you will know precisely what kind of disorder you get in the wave function structure. Okay, so you could take a look at the paper and write me if you want more details. But we want to build a Fibonacci quasi-crystal. We even have already the design, but we have been trying other things. We didn't get there yet. And it will be very difficult to see this fractal spectrum because we don't have a resolution. The broadening is still too large. We couldn't get one design that would allow us to see the things we are talking about in the paper that we have put yesterday on archive, but we are looking into it. But people have looked at the Fibonacci quasi-crystal with the photonics. There are beautiful works in the group of Jacqueline Bloch, and also Samite. There are some works on that.
Okay, thank you.
Thanks for the question.
Fernando, can you?
Okay, okay, I can ask my question, or should I write to her later? Can I ask my question?
Yes, please.
Okay, good. Oh, Christian, there is, as always, incredible talk. Thank you very much. There is always that I have been willing to ask you since I first heard you talk about this fractal calculus. Is something very, it's like say elementary about that. How is the thing of dimensional analysis when you do fractal calculus? I mean, usually when you do usual calculus, you derive a quantity and you somehow, the quantities in physics, they have definite dimensions like length, time, and so on. So when you do fractal calculus, how you go around that? I mean, when you
Yes.
is there a problem concerning the dimensional analysis when you relate quantities by this kind of fractal calculus?
Yeah, so if you do, if you go to our paper on archive, you can get a notion how to do the dimensional analysis. Yes, because the G, so if you do, let's say, Gx dt, right?
Exactly.
This is x over t. So this is first derivative, this is x over t in dimensional analysis. It's velocity, right? Now, if you do a g beta x, gt beta, where beta is not 1 and it's not 2, so you will have t to the beta in your dimensional analysis. So we do it at a certain point just to understand. Yes, absolutely. The fractional derivative enters as an exponent in your dimensional analysis.
Okay, I'll take a look at that. Thank you.
Yes, you're very welcome.
Okay, everyone, thank you for your questions. And let's thank you again, Professor Cristiane, for your nice presentation. Unfortunately, we have to move to the closing section, so we don't have too much time.
Thank you very much for the very good questions. You had so interesting questions. Thanks a lot. It has been a great pleasure to be with all of you.
Thank you very much, Professor.